slope, or determine the yield strength. Last time, right, we talked a little bit about residual stress or residual strain, sorry. I think, right, we talked about that. Is that familiar? Okay, just really quickly again, and this will come up in the homeworks that you get to do. But if we think about residual, let's just do this. Okay. Let's say that we have a wonderful stress strain curve that looks something like this. A couple things happen. Okay, so first we would say, okay, the yield strength, let's just say that this is 0.2% because, you know, it doesn't have to be in the same spot, but let's say that this is the 0.2% right here. So now we have our SY, like that. If we load such that we're going up and we're going up and we stay less than the SY, then we just come right back down when we unload. If we go up, and we go beyond the yield strength, that's where we get into the plastic regime. And let's say that we go up to here, like this place. When we release the load, we follow the slope associated with the elastic modulus, down back here, and this becomes the residual strain. And we talked a little bit about strain hardening last time as well. The new yield strength of the material is up here. Okay. So did it die? No, good. It's still working. I'm glad it's still working. So if you go up this, so you say, okay, here's my sample. It's a little stretched out. You're like, hey, I gave this bar to you, and you're giving it back to me with some extra length. What's going on? Well, maybe you plastically deformed it on purpose. Maybe it was your kid and like they were having fun, they jumped on it or something, and now it's not the same shape. So when you do that, you've got now this new level of stress that it can handle before it would start to yield. So this is the new elastic curve. So this is very useful property, obviously, for treating the steels and some of the metals, because you can simply stretch a material to give it additional strength. Of course, you need to anticipate that there's going to be a change in the length or the change in the dimensions when you do that. So the material is now hardened. It's got a higher strength. Any questions up to this point? This is kind of reviewish. Okay. And this was reviewish too. Here are a bunch of yield strengths of materials. And we also mentioned that these yield strengths are not set in stone or set in steel. All right? They can depend on the processing of the material and the composition. A steel can have a lot of different types of additives or alloying elements to it. And the elastic modulus does not change, but the yield strength can change significantly. Okay. So we've just covered these, and yeah, we talked about how we handle this 0.2% offset. Okay. Yes, that's all we need to know there. Okay. Moving on. Ductility. All right, so this is the degree to which a material can sustain plastic deformation under tensile stress before failure. All right, that's a fancy way of saying, hey, how far over does that yield, that stress strain curve go before you fracture? And if you have a material that does not plastically, like if you just keep it in the elastic regime. So some of the rubbery materials, for example, they can strain quite a bit, and they can, even though they have a low elastic modulus, because they have this ability to go for a lot of strain. Okay, they can still absorb a lot of energy. And we talked about bunkers last week, I think, or last time we met. In terms of characterizing the material, there are a couple ways to report ductility. One is how much does it elongate, okay, when it breaks. So LF would be the fracture length, L naught would be the original length, and so you take the delta of those and you put it over the original length and you times 100%, and that's percent elongation. Another way is to look at the reduction of area. So a lot of the brittle materials, like the glasses and things, ceramics, or high carbon, like cast iron, okay, those materials will essentially have a brittle failure, right? So if I take a piece of chalk like this, and I don't think I'm strong enough to, no, I'm not. I'm willing to meet my balance. So I can't do a tensile test with my arms, and I have issues with my shoulders. Some of you might be able to, but I'd argue that it's going to be pretty hard to do a straight up like tensile test on this. One way though how do you break chalk though? Okay, you throw it. Okay, all right, or I bend it, right? I snap it, right? So when I snap it, that actually, so we'll cover this when we do bending. Bending actually puts axial stresses, okay, and they vary as a function of distance from the middle center line or the centroidal line, okay, the neutral axis or the longitudinal axis, depending on how people define it. But if I bend it, I'm actually causing a whole bunch of different tensile stresses, okay, in that material. So if I bend it and crack it like this, it's a brittle material, and if you look at it, it's really quite flat. Okay, the cross-sectional area has not changed much, and if I were to, well, I had to do a tensile test. If I were to also figure out, a tensile test, how much this thing stretched, it'd have very low percent elongation. Okay, that's a brittle material. So ductile materials are just the opposite. So think of your rubber bands. So here's a stress strain curve with all of its features, and again, here's that stress strain curve that we showed, where you have a ductile material that goes on for a little while, and you have a brittle material that just is pretty abrupt. And here are some pictures that show resulting tensile tests of aluminum that is pretty ductile, and you see the necking behavior, whereas this cast iron has this fracture surface that's rough, and there hasn't been much elongation, and there has not been much reduction in area. Yep. Okay. Now, we're going to talk about two material models, the linearly elastic, perfectly plastic, and the linearly elastic, linearly plastic strain hardening model. Okay? So maybe not things that go right off your tongue, but I think linearly elastic, perfectly plastic could be like a fun rap song. Okay? Like, it's linearly elastic, perfectly plastic. I got credit cards like that, or something like that. I don't know. But these simplifications capture behavior that allow us to make predictions about, well, how much energy might be stored for a given amount of strain in a material, and, or how much energy might be stored in a structure, okay, given its volume and given its geometry. They allow us to also, in design and mechanical components, you'll learn, so we talked a little bit about residual strain. You'll also learn about residual stress, okay? And like this combination of these two together, and they go hand in hand. Using these types of models, it's nice and pretty straightforward to be able to calculate what residual stress or residual strain you might have in your system when you unload it. Using these models, it's helpful for looking at fatigue-based analysis. Okay? And it's useful for handling systems where you preload bolts and nuts. And again, you'll do that in design and mechanical components. So these models are helpful. So the first one, the linearly elastic perfectly plastic, as you can imagine, and in both of these models, there is still a region that's got an elastic modulus for its slope. And it captures the yield strength, and at that yield strength, it then just goes horizontal. Okay, that may not be a perfectly horizontal line, but it's supposed to be. That's, so you see linearly elastic, that describes this portion, and then a hyphen says perfectly plastic. Perfectly plastic means that the material kind of almost unrealistically, but good enough for many of our intents and purposes, keeps stretching as long as you keep applying the same amount of stress. Right? So once you go plastic, it's like bubble gum that you're pulling out of your mouth, right? You don't have to apply more force. You just keep applying displacement with the same amount of force, and it just keeps stretching. That's perfectly plastic. Okay, it does not capture the ultimate tensile strength, right? The ultimate tensile strength was back here, okay? This is the ultimate tensile strength, okay? Where it reaches a maximum. So it doesn't capture that. It doesn't capture strain hardening, right? So you saw in a second ago, or minutes ago, I'm probably going too slow today. It's okay, right? You saw that in order for strain hardening to occur, you had to have an increase in the yield strength, right? But if I go along that perfectly plastic regime, my yield strength, it can't go above that yield strength. That's it. That's the maximum stress that that material can withstand. And in DMC, if I were teaching it, you would hear me say this a lot, that the material just cannot handle more stress than the yield strength. That's it. Maxes out. Okay? The material will give, it will plastically deform rather than have a stress that increases. Okay? So the maximum stress is the yield strength. It does allow us to capture residual strain from unloading, though. Okay? So if you go over to the right, you can move back down. Okay? Or sorry, you can move back down that much, and then you can figure out what the residual strain is. The linear elastic, linearly plastic model is another simplification for data you might get from a stress strain analysis, or from material tensile test. And it does capture elastic modulus, just like the linear elastic perfectly plastic model does. It does capture the yield strength, just like the perfectly plastic model did too. And it does capture strain hardening, right? Because if I go further up, right, then I'm going to get a higher stress. And both of these models, I may not have said this, typically they do have an X that marks fracture, okay? So when that curve ends, that's it. You're done in terms of, the material has failed in a catastrophic or in a breaking type way, okay? Now, the slope, though, here in the strain hardening region, or in the linearly plastic region, is going to be less than the elastic modulus. Okay? And that often, well, we'll give it a slope called S. Okay, so let's do a little bit of example work. We have a linear elastic, perfectly plastic material with an elastic modulus of 210 gigapascals. What material would this be? Probably, if I say it's 210 gigapascals, you say? Steel. Yeah, all right. Okay, and it has a yield strength of 200 megapascals. And you're like, if I just give you that yield strength, you'd be like, I don't know what in the world material you could have. That could be aluminum, that could be steel, it could be carbon fiber, it could be a lot of different things. Well, maybe, I mean, carbon fiber has typically higher strength than that, but you get the point. Okay, if we strain the material to 0.3%, what will be the residual strain when the load is released? Okay, so we already did this pretty much, okay? But here's maybe the matharoonie. So you've got a slope E, and this is a perfectly plastic material, and we've got to figure out where it goes plastic, though. Okay, right? I don't know. You know, I don't. You know, we got to figure out where it goes plastic, because you don't see that, right? It says we're straining the material 0.3%, right? But we can figure that out. We can figure out what the yield strain is. How do we do that? Well, we know what the yield stress is, or the yield strength is, and we need to figure out the associated strain with that yielding. So we got our strain we're trying to figure out the strain at the onset of the yield. And so that is going to be simply the yield strength divided by elastic modulus, right? I'm just plugging in this 200 megapascals for the yield strength over right here, right, to figure out what the yield strain is. Why do I need to know that? Well, if I'm figuring out residual strain, right, if I go plastic like at 0.1%, right, then I know that you know, I'm gonna just like keep going for a while. If I'm going all the way up to 0.3%, right? So here we find out that it's 0.095%. Okay, so around 0.1%. So that's really right here. We're going all the way to 0.3. So what do? We just draw this line out. This is the perfectly plastic line, and we go all the way to 0.3. Okay. Now, when we unload, we're going to go back down that line right here. Okay. What is the backtrack? Well, we're going again. We go down with the slope of the elastic modulus, and we're at the yield strength 200. So we're going to go backwards 0.095%. Okay. So yes, we calculated out what the yield the yield strain was here, right? And we drew it out, and we drew this out, right? But this is 0.095 actually is going to be subtracted away from the 0.3%. So the residual strain is going to be essentially this max strain minus the yield strain, or the strain at onset of yield. So you do that simple math, and we get that it's going to be something like that. Any questions on that? Any questions? Thoughts? Criticisms? Straightforward? Okay. Most of these things are pretty straightforward. Question is, you know, getting the right image in our minds, figuring out what the geometry looks like. And we'll talk at the end of the class. We'll talk about a process that you can use for problems that are a little bit more involved. This is purely based on a material. This is like a material question. Okay, so you don't have to use like this whole process, but it can be a little bit difficult to figure out what's going on. So you'll have a question in the homework that does this same type of thing. And then there'll be another question, okay? And there's a hint there, and I guess nowadays, since I'm trying to get the videos done for those of you who, you know, just want a little extra explanation of things, you know, so I'll try to get that out Thursday for everybody. But here will be another question. Okay. This is actually based on that same, this is from that same exam one where you had the acrylic sheet hanging on 2 cables. That's the same question. Or same, it's another subpart of that question. Okay, so now let's do something similar with a linearly elastic, linearly plastic material. This is definitely more complicated. Okay, so we have an elastic modulus, and we have a strain hardening slope of 20 gigapascals. And we have a yield strength, once again, of 200 megapascals. So this is what the model looks like. And we go ahead and we say, all right, this is, there's really nothing that wrong there. This is the yield strength. Okay, this is, I just put it up there. It should really be down here. That's all that's happened here. So this is the, once again, the yield strain, or the onset of yield happens at epsilon y. And then we go up to some level. All right, and this, you know, this is going to go up to 0.3% strain down here, and it gets up to some, I don't know, new stress level. Okay, that's going to be, and that's going to be the maximum stress that we get to. And I called it, I guess I called it S nu or S nu B. Nu B being the difference between the yield strength and S nu. Okay, you see there's a little gap there. So S nu, this point, is going to be equal to the yield strength. And, you know, sometimes we write sigma sub y, sometimes we write S sub y. S sub y might be a little more confusing with these linearly elastic, linearly plastic material models, because the because S is often what we'll use for the slope. Okay, so we have lots of S's. So this S is the slope of, you know, of this plastic regime. And this one's straightforward. This one might be a little bit trickier, right? So what we're saying is that we have the slope, right, times the run, right? The run is epsilon max minus epsilon y. So that will give us the extra rise. That will give us the S nu B, right? That we can add to our SY, to our yield strength, to get S nu. So we can calculate out what S nu is. And that's you know, that's interesting. Okay, so that answers this question here. What will the new yield strength of the material be? Because remember, we load it, and then if we unload it, it comes back down. There's going to be a lot of, or there'll be some residual strain. Okay, and it's going to go from this S nu down to the 0. So it even goes back further, right? It goes back further than epsilon y, because it's got a larger run that is going to go back down. Okay? So, but this new strength is the 241 megapascals. Obviously, it's higher than the yield strength. When we go back, right, this would be, so the distance from here to here is going to be our epsilon r. That's going to be our residual strain. How do we calculate that? Well, we need to figure out what this value is, and we can do it by saying, okay, epsilon max, and then how far am I going back? Well, I need to know the run, so I can say, all right, and to figure out that run, I can use this this negative rise, okay, over the elastic modulus, and that will tell us how far back we're going. So epsilon r will be this distance here. So when we do this out, of course, being careful with the units, because we got megapascals and we got gigapascals and we got percentages. So try to be very careful with all those units, and we get that the residual strain is as follows. Any questions on that? Yes. Or you're raising your arm,
sorry.
stretching. Okay. So what would an exam question look like? Well, actually pretty similar to this kind of thing. If you look at previous exam questions, you'll see that it's like, hey, okay, Maybe it would probably be more of I start with a bar and I say, okay, what's the stress in the bar? And you calculate it. And it's like, hey, is it less or more? Or, you know, that. And so that's a good point. Right? Okay. You hope, right, that if I ask you to calculate the stress in a bar and I tell you that the yield strength of the material is blah, you hope, right, that stress in the bar is less than the yield strength. Right? That's what you hope, because then everything's hunky-dory in your elastic regime. But if you calculate a stress that's higher than the yield strength, right? And I say, okay, what's the, and I say, okay, so what would be the, if it were just purely linearly elastic, what's the yield strength? Bam. But then if I say, oh, no, it's a linear elastic, perfectly plastic model, then you say, oh, no, cannot go higher than that yield strength. So yes, even though like I would predict a higher stress, like no, because of the material model involved, I can't. It has to be this yield strength, okay, for the perfectly plastic. But if it's a linear elastic, linearly plastic model, like, now I got to go up that curve, and I got to figure out, okay, where I am on that curve. And then if I say, oh, calculate the residual stress, you'd be like, oh, I don't know how to do that. Okay? Actually, the residual stress in this case, I should probably point that out. When you get back down, so you have this residual strain. Okay, so I ask you to calculate the residual strain. How much stress is in that material? If I'm back down here, at this point, how much stress is in that material? Yeah? 0, right? There's 0 stress. Okay, so there's no residual stress in this case. This is for a nice uniaxial loaded bar. I stretch it, plastically deform it, it goes back just a little bit. And then I let go, and there's no stress. It's just strain. But when you have something like you bend, like a beam that you bend, okay? So like if I had a paper clip, if I were a good professor, I'd have like a paper clip right now, okay? And I'd bend it, paper clip. I need something to break. I have one. You have one? You want to sacrifice for the sake of engineering? Who said that? Okay. Good. It didn't poke my eye out. All right. Oh, look, this is perfect. You already got a ton of residual strain in this guy. Okay? See that? That's deformed. There's all kinds of residual strain. And even in bending, right? So there's not a whole lot of, like, I'd have to like work really hard to be able to get residual strain in bending. Or in tension here. Okay, but you see how there's all this curve stuff, and you think, okay, that's just got residual strain in it, and it does. Okay, but parts here are now in. So if I've got a beam, all right, and we're getting ahead of ourselves. If I've got a beam and I bend it, does the top of that beam, does it go in tension or does it go into compression? The top. If I bend downward, does it go in tension in the top or compression? Tension in the top. In the bottom, it goes into compression, right? So what happens, and this you'll cover in DMC, is if I just do elastic, so I just bent it on purpose, right? But if I do elastic, I can do elastic and it just goes back. But if I cross the local thresholds for yield strength, then I get plastic deformation, okay? And I actually get tug of wars. So what's happening is that I yielded some of the material, okay, in tension, and I also might have yielded some of the material in compression. And I end up with kind of residual stresses inside such that now part of the material wants it to go back to its original shape. And so the top now is going to be in a residual state stress of compression, and the bottom is going to be in a residual state stress of tension. It works the opposite, because the bottom material is kind of like, hey, you want to go, or some of the material in the middle, like in the middle that didn't yield, it's still elastic, it's still perfectly happy, but it's not happy because it's got some strain, or it's got some residual stress in it. Okay. Anyway, thank you. You can pick this up afterward. All right. Let's go on. Okay. We love springs. The wonderful thing about Tiggers is Tiggers are wonderful things. Their something is their tails are made of springs, I think. Is that how it goes? So. Great. Okay. So, how does Tigger get it done? Tigger's tail cannot be breaking every time. It cannot be yielding every time. Otherwise, he would be very not Tiggery. Okay? So we can think again about springs. And with these springs, we know that there's a relationship between the force and their displacement. Okay? And we know that we can store energy in a spring, 1/2 k delta squared. Or, right, another way that people look at it, what's the energy under this curve? Or what's the area under this curve? That's the energy, right? And it's going to be a half of the rectangle, right? That's the area under that triangle. So I think this is the formula everyone loves because it's just like, hey, 1/2 k delta squared. I sound cool. But 1/2 f delta is actually also true. And now, what do? We begin to think about the parallels, okay, to having a material element. If we have a material element, okay, it is kind of like a bar, right? But it has a really small cross section and a very small height. And we can begin to think of there's a relationship, okay, between the some force, maybe delta F, and the stress, the axial stress that we have in the cross-sectional area. Okay, so these equations, right, these are just the definition of stress and the definition of strain. This is the definition of cross-sectional area. And we can think of this energy as being essentially this parallel that we had down here for our big spring, where it's 1/2 F times delta. This is going to be 1/2 delta F times delta. Okay. And so that internal energy, what it comes out to be, is going to be, all right, what's the delta F? All right, we have sigma times delta A. Delta A is delta X, delta Y. So that's this component right here. And the delta is just the epsilon times delta Z. So we now write that this whole energy that we have in this element, delta U, is equal to 1/2 sigma epsilon, right? We're just rearranging things. Sigma epsilon. And what's this? That's the change in volume. Length times width times height. And so for a material element, we can say that that change in energy is going to be 1/2 sigma epsilon times the delta V. All right? So we went from a Tigger to like a micro Tigger, okay? Or you can think, hey, we took just a little piece of his tail and we're looking at that small material element and we're saying, hey, that is the energy that's associated, okay, with that particular element. Now, what are the units here? Well, the units are still kind of what we know and love in terms of units, right? Those are going to be in joules or Newton meters, okay? But as you can imagine, we can then take out the volume, all right? And if we divide by the volume, we get something called strain energy density per volume, okay? So now we're back to sigma times epsilon, and sigma times epsilon units are pascals, right? Because epsilon is U-dimensionless. we have now Hooke's law for a linear elastic material. Sigma equals E epsilon. Okay? We can rewrite that epsilon is equal to sigma over E. And then now we have a quantity that we call the elastic strain energy density, right? Just substituting the epsilon back in there. So here are some units to keep track of things, like we were talking about. And we went ahead and did that substitution. And the strain energy density, right? This is kind of a wild one, but this is going to have units. Well, we already know it has units of pascals, right? Because that has units of pascals. We just did a substitution, but this is still the same quantity as this. So it's units of pascals. Or you can say, oh, that's pascals squared over pascals, which is going to be pascals. This quantity is what we call the modulus of resilience. Okay? And yeah, it's technically the proportional limit that we use here, but for our exams and things, you're just going to substitute in the yield strength, okay? Because I'm not going to distinguish that. But I can say proportional limit, that's fine. Okay? So it's the area under this line, okay, because it is linear with slope of the elastic modulus up to this location. And yes, like I said, we often use the yield strength instead of the proportional. Okay, any questions on this? So what's interesting here is that this is another material characteristic that we can use to understand how material will respond. Okay? So yeah, I mean, do I take an infinitesimally small element and do little tests on it? No, right? This is probably going to be put in the tensile tester or the material testing machine. And I'm probably going to stretch a bar. But I'm going to back calculate the stress and the strain associated with the yield strength or the proportional limit. And then we'll have a quantity that's in pascals that we'll call modulus of resilience. And this will give us some idea of how much elastic energy the material can store. And different materials will have different moduli of resilience, just like they have different elastic moduli. Any questions on that? Yes?
Is there always going to be a linear relationship between stress and strain?
Yeah, so for our class, yeah, but when you start using the rubbery materials, they get kind of complicated. I mean, one thing that we've also kind of tossed out the window is that these materials are independent of time, right? So it doesn't matter if I apply some stress and I wait a day, apply a little more stress and wait a day, right? But we know that materials can creep, right? And so if you have a stress on a material for a period of time, yeah, you might creep a little bit, as they say, right? You might get some extra strain just based on the fact that you're loading it. And with the polymers, this is particularly prevalent. Steel's not so much. I'm glad that our steel bridges are not creeping that much. I mean, there's going to be creep, but it's not so bad. Yeah. Other questions? That was interesting. Okay. So, modulus of resilience has a friend. It's a tough person. Okay? Modulus of toughness is the total area under the stress strain curve. Okay, so now this gives us an idea of how much energy the material will be able to again, we've already talked about this a little bit, but now we're introducing parameters that are specific to specifying materials or their characteristics. So this is going to be the total area under the stress strain curve, meaning until you break. And we know that it's got to be larger than the modulus of resilience, and it's kind of often a two-step process. Often you're going to want to calculate out the modulus of resilience, and then you're going to take a look at the area under the rest of the curve to get the modulus of toughness. Okay? So in terms of what the modulus of toughness represents. It represents the elastic strain energy plus the plastic strain energy. Okay? So again, it's just another characteristic. Typically, we don't want to be, pushing the limits for this class. Like, we're typically not going to want to design for the plastic regime. But, if we have questions on material properties, of course, we can stretch things. Okay, so here's another example. We have a linearly elastic, perfectly plastic material with an elastic modulus of 210 gigapascals. Has a yield strength of 200 megapascals. If the material fractures or breaks at a strain of 0.3%, what are the modulus of resilience and the modulus of toughness? Okay, so this is another example of where having this nice simplified model allows us to make calculations that aren't too difficult. Do not discount the fact that you can use your brain if someone gives you a stress strain curve. Okay? It doesn't look like this. I mean, I know I'm going to a more complex problem, but graph paper is a wonderful thing. Hibbler would have examples, and I think if you look at, I guess it's a moment digression. If you want to look at example problems from Hibbler's book, you can go on Canvas, and I've got prior assignments that we used to assign from Hibbler's book, okay, with solutions. So I think one of the early assignments is talking about calculating out modulus of toughness and modulus of resilience, and it has it pretty much on graph paper. So what do? You count the boxes of graph paper, right? You can count the boxes, and you don't have to do any integration, right? Or no calculation. Well, you have to do some calculation. You have to count, right, and figure out what the area is. So anyway, here though, this simplified model allows us to do it in a kind of geometric way, right? We know that we have a triangle over here, and we know we have a rectangle over here. And what we have to do is calculate the area under the triangle. We have to calculate the area under the rectangle. And when we do that, we can figure out what the modulus of resilience and the modulus of toughness are. So UR, right, R for resilience, UT, not a place in Texas or Utah or some other place, but it's the toughness. Any questions on this? All right. This is the one that has also been, I think the exam from maybe 2022 has one like this that people did not like, or at least they did not do very well on, okay? And that was when you use the the linear elastic, linearly plastic model, okay? It's a little bit harder because, yes, you have a triangle, but now you have, what is this shape called? Trapezoid, right? So there are different ways to solve for the area of trapezoids. One is to say you can take the average of this and this length times the height. Okay, that will give you the area of the trapezoid. Right? Or this particular trapezoid looks like a rectangle plus another triangle. Either way, right? You've done geometry. You can figure out what the area of this object is. Okay? And if you want, there's some code that allows you to do this quickly as well. Any questions on that? Okay. All right, so you have some opportunity to do this type of work, okay, and some more opportunity to do this type of work. Okay, there's a triangle, there's a rectangle. Okay, no, the units. All right, are people having fun with the units? How many people have used Google now to solve your problems? Okay, great. I'm happy. Thank you for confessing. I didn't teach people. I didn't show people that. And at the end of a semester, I was like, hey, you can just do this in Google. I'm like, what? So anyway, good. I'm glad you're using Google. You will not have Google on the on these exams. All right. But do any of your calculators keep track of units for you? There must be some calculator. They don't? The old HP 48G did. It was slow as anything, but I think it did do the units if you wanted. I may be lying. So look it up, HP 48G. That's a classic. All right, that's what I used, and now I'm extinct. All right, so, well, I'm not extinct, but I think not many people use. Does anyone use an HP graphing calculator nowadays? Oh. Does anyone know what HP stands for? All right, good. Hewlett Packard, yeah, okay. They made some great calculators, but TI pretty much dominated it. Anyway, and now we have Desmos. No Desmos either, of course. But feel free to use Desmos for the problems. Okay, so the last material property, I think this is the last one we're going to cover today, is something called Poisson's ratio. So if I take this material, right, and I stretch it, what happens to the cross-sectional area? Like the cross-sectional area, right? We haven't really talked about this. If you take that gum out of your mouth, right, I talked about how, oh, that's just like really nice and plastic. Oh, you want to volunteer? Oh. All right, but if you take it out, what's going to happen? It gets thinner, right? It gets thinner and thinner and thinner as you stretch it. Well, we have a parameter for that. Okay. The ratio, okay, or the negative ratio of the lateral strain over the longitudinal strain is called nu, or the Poisson's ratio. Okay, so let's break that down. Here is our beautiful bar, and these are my drawings, which are, how do you say it? Hopefully they make you feel good, because you can draw them, and then yours probably look better than mine. Okay, so it's a moral booster, okay, morale booster. All right, so if I take, this is the original cross section, or this is the original cross section here. I stretch it out. This is very much exaggerated, but it gets thinner. So this is the new profile. Okay, it's nice and it's thinner. Okay. What we're saying is you're going to have some change in the radius, for example. Right? It's gotten smaller. It originally had a radius of r, okay, and now we're going to have an r minus delta r, okay, for the new radius. And it's tricky because the change in diameter, it can be, that's like this delta d is equal to 2 times this delta prime here, okay? Or here's another, this is a nice, kind of nicer view, right? You can see that you have a delta L and you have a delta L prime, okay? And that is going to be related to this delta L in this direction. So we've got a longitudinal strain. Okay, the longitudinal strain is going in the direction the force is being applied. The latitudinal strain, all right, is going to be going orthogonal to that direction that we're pulling. So if I pull like this, the longitudinal strain is that positive or negative? If I'm pulling it apart, longitudinal strain is positive or negative? Is it in tension or compression? That's how one way to think about these strains. I'm pulling it apart. Is it a positive or negative? Positive, okay? Positive because I'm stretching it. Tensile stress, tensile strain, positive. Tension. Compressive stress, compressive strain, negative. All right? So I'm pulling it apart. That's going to be positive strain. Then I look at the cross section. Is that strain positive or negative? For a normal material. Not a metamaterial, okay, but a normal material. It's going to be negative, right? Because it's contracting, okay? it would be a compressive force or compressive stress if there was one. Okay, now it turns out it's actually doesn't there's not a stress. It's a strain. Okay, and that's negative. The Poisson ratio for homogeneous isotropic materials is always positive. That's what that negative sign does. Because if I apply a positive longitudinal strain, I expect a negative orthogonal lateral strain. And then put a negative sign in front of it. Okay? So Poisson ratios are positive. So for a cube, what we'd have is epsilon x is equal to 2 delta L, okay, if we have this delta L on either side over L. Epsilon y is equal to this minus 2 delta L prime over L. These 2's and these L's cancel out. These, we could say x is going to be our longitudinal, and y is going to be one of the orthogonal. You see that? This is the x direction, this is the y direction. Okay? And we would have this minus delta L prime over delta L, and that's going to be a minus nu, right? So minus nu, because one of these is positive, right? One of these is positive and one of these is negative. So this is going to be a negative quantity, so it's got to be minus nu, the Poisson ratio, which is a positive quantity. So it's negative. Questions? Yes.
Is it also dimensionless?
Yes. Okay. You've seen this behavior before, but then now this is just a little, for something like that, blah, whatever. It's a little bit of a mind bender, though, okay? Because you got to think, okay, there's positive, negative, and keep track of the sign. Here's a little bit more about it, okay? Look, normal stresses, sigma x, sigma y, sigma z. Normal strains, epsilon x, epsilon y, epsilon z. Isotropic and homogeneous materials, that means that, I can take a cube and it's going to behave the same way if I pull it in x, y, or z. Got Hooke's law, which we love, right? And that's just sigma is equal to E, all right, E epsilon, but rearranged. So now we have longitudinal. And we have a Poisson's ratio, that the lateral is equal to minus nu times epsilon long. So all these things on longitudinal. So all these things this one is the only one that's new. That's the only new. Remember, it's new. And it's new. Okay, I'm not very funny. I haven't made that joke before, I don't think. Anyway, my kids won't appreciate. My kids, you're showing off, Dad. They don't appreciate my nerdiness sometimes. All right, so we have nu as being that ratio of minus the epsilon lateral over the epsilon longitudinal, but that's just rearranged. Okay, look at this. Okay, so now if I just had a longitudinal strain, then I can think of it in terms of a longitudinal stress over E. And now I have an orthogonal in the y direction. I have an orthogonal in the z direction, right? And I can take this epsilon x1 and I can multiply by minus nu, and this is the expression I get. Similarly, I can do it in the 3 direction or the z direction. I can also do it in the 2 direction or the y direction. All right? And this is what we get. Imagine you've got superposition, right? We talked about superposition, right? I can put one force and I get a displacement. If I change that force or add another force, right, I get additional displacement. Same thing can happen with stresses and strains. Okay, if they're in the same direction, right? Same direction, same face, right? Don't add a sigma x to sigma y. That's a no-no, right? Don't add a tau x, y to a sigma x. No, right? We got to keep them straight. But you see this? I've got a strain in the x1 direction over here. Okay. I've got a strain in x over here. I've got a strain in x over here. Okay. And I can kind of put them all together, and I can write that, oh my goodness, if I have a stress over the epsilon E, that's going to give me this epsilon x1. If I have a stress in the y direction, I can relate that to strain in the x direction through a Poisson ratio. And if I have a stress in the z direction, I can relate that to an epsilon x as well. Okay? So now what we're seeing is something that we can consider to be a superposition where stresses in opposite in orthogonal directions can actually lead to contributions in the same direction for strain. So, is it true that Hooke's law is still valid? Yes, of course. But Hooke's law, the way we wrote it out, it applies to the very specific case where it's uniaxial loading. What does uni mean? One. Axial along the axis. So Hooke's law, you have to be careful with it. Sigma equals E epsilon is this universal beauty, but it's really only for uniaxial loading, which is quite relevant to a lot of the problems we do in this class. Okay? But if you have a material that has a Poisson ratio, which pretty much every material does, and there are stresses applied in 3 dimensions, when you look at the strains, you've gotta account for these additional stresses. Right? So that's kind of a problem. And if you want to go matrixy, it looks like that. Okay? So this epsilon x, right, here on the left side, 1 over E times this big quantity. I've got 1 times sigma x minus nu times sigma y minus nu times sigma z, just like I had here. Right? And this matrix is going to give us the relationship between the stresses and the strains. And if someone said, you know, the way this is calculated is I can calculate out the stress or the strains here if you give me the stress state. Now there are no shear stresses here, not yet. But at least if it's got just a triaxial state of stress, meaning they're just normal stresses, I can go from these normal stresses to these normal strains. If I want to go the other direction from normal strains to normal stresses, I've got to take the inverse of this matrix. Okay, multiply it by both sides. Everyone happy? Don't worry, there won't be much linear algebra here. Okay. The last thing in the last 4 minutes is here's a general approach to solving problems in mechanics. This comes from Crandall, Dahl, and Lardner, the book that I used when I was taking mechanics and materials. Here are the 3 steps they suggest. And this is a general approach. Do equilibrium. Look at geometric compatibility. And remember the force deformation relationships. These 3 pillars can help. So if you're given, hey, I have a problem where I have a bar, I have some force, and I have some displacement, you can even break up your page into equilibrium. You can then look at a column for geometric compatibility and another one for the force deformation relationships. And then you can combine, you work through these to be able to solve for displacement or whatever it is that you're being asked to solve. So when I took the class, the professor went up and would essentially say, look, this is the force category. This is the geometric compatibility category. These are the constitutive relationships. And it turns out when you do something like multiphysics later on, it's a good idea to be able to break it up into these, compartmentalize into these 3 areas. Okay. So here's another problem. What are the lateral strain, change in radius, and change in diameter? Okay. So now that we know something about the Poisson ratio, and 0.3 is a common one, okay, we can go ahead and we can figure out, using these three pillars, using this information, how the change of radius is related to the force that's being applied, the Poisson ratio, and dimensions, diameter, area, and the elastic modulus. Okay. And then these are going to be the strain, the lateral strain, and the change in the radius, and the change in diameter. All right. So that's pretty much it for today. Well, you can there'll be some more examples, but I hope that that we've developed some type of appreciation for the additional characteristics that materials have, a little bit of appreciation for how we measure them, and a little bit of appreciation for how we solve these types of problems. Thank you. See you on Friday. Oh, attendance. Attendance. It's 2 minutes. 2 minutes. 2 minutes. Okay. Nope, not that. Hold on. That's it. All right. Yes. Okay. Take your turn, please. Yeah, please. We've been getting a number of emails about, hey, I was here. Here's the photo. Please upload it in the next 10 minutes, please. Right? 15 minutes might save you 5. What is the Geico commercial? Yeah, there you go. All right. Thank you.